Here at the center, and I'm pleased to welcome you to the 5th Chatham Marconi Speaker Series presentation of 2025. Significant advances in artificial intelligence, we'll say AI from now on, have marked the past decade as new knowledge and techniques have emerged. One of the many applications that are affected by recent AI advances is wireless communication networking, which has been dramatically enhanced compared to the state of the art as it was 5 to 10 years ago. Dr. Wyglinski will discuss how AI and SDR, which stands for software-defined radio, can be co-designed together to solve problems in challenging use cases. He'll then examine several of these cases studied extensively at Worcester Polytechnic Institute, including cognitive radio-based satellite communications, radio frequency fingerprinting, and smart jamming of 5G networks. Dr. Wyglinski is the Associate Dean of Graduate Studies and Professor of Electrical and Computer Engineering at Worcester Polytechnic Institute in Worcester, Mass., as well as the Director of the Wireless Innovation Laboratory at Worcester. He served as the President of the IEEE Vehicular Technology Society 2018 to 19, received his Bachelor of Engineering and PhD degrees in Electrical Engineering from McGill University, and his Master of Science degree in Electrical Engineering from Queen's University in Canada. His current research interests are in wireless communications, cognitive radio, machine learning for wireless systems, software-defined radio prototyping, connected and autonomous vehicles, and dynamic spectrum sensing. Dr. Wyglinski has published over 50 peer-reviewed journal papers, over 135 peer-reviewed conference papers, and 3 textbooks throughout his academic career. He's been sponsored by government agencies and industry, including the National Science Foundation, Office of Naval Research, Air Force Research Lab, MIT Lincoln Labs, Toyota Info Technology Center, Verizon, MITRE, Analog Devices, and Raytheon. Following his presentation, Dr. Wyglinski will answer your questions. And it is now my pleasure to introduce Alexander Wyglinski.
Thank you. Thank you. Thank you, everyone. Thank you, Rob, for that warm introduction. And thank you all for having me here today. It's exciting, something I've been looking forward to for months, ever since the kind invitation to present. Like as Rob mentioned, my name's Alex Wyglinski, so I'm both the Associate Dean of Graduate Studies, so that's my administrative hat, and then my research and teaching hat is Professor of Electrical and Computer Engineering, and I also run the Wireless Innovation Lab at Worcester Polytechnic Institute. What I'm going to be talking about a little bit is how the worlds of like artificial intelligence, so AI, machine learning being one form of AI, communication systems, which I'm in the right place. This is very exciting to be here. And software-defined radio, which is sort of like a technology that it's at the core of all things that I do with respect to my research and teaching activities at WP. I'm going to describe how all of these come together, okay? First of all, I want to acknowledge various funding sources that have been incorporated in some of the results I'm presenting here today in this presentation, including work from NASA, the Glenn Research Center, their grants, so that's with the satellite communications project I'll talk a little bit about, MIT Lincoln Laboratory in Lexington, as well as the Air Force Office of Science and Research DURIP grant that support a lot of the equipment purchases that I do my research with. Okay, so since we're in a museum type environment, I'm going to go down my own history, my own memory lane, if you will, okay? So first of all, this idea of AI, there's been a lot of hype over the last 5, 6, 7 years, but this idea of AI has actually been around for decades, right? It just happens that with a lot of things, AI kind of gains traction and something really innovative happens, and there's a lot of excitement and buzz ever so often, every 10 to 15 years, okay? And then in between, when AI does not fulfill its promise of like taking over humanity, it's like, oh shucks, it didn't work, blah, blah, blah. And we go into something called an AI winter until the next big thing 10 to 15 years later. Okay? So luckily in my lifespan as an academic, I've seen at least 2 of these AI peaks in terms of activities related to my wireless communication research and teaching duties. Okay? So if we go back 12 years, okay, this was, and as I was telling Rob, like, you know, this idea of having a WPI template for slides, this is the reason why, because that's what a WPI, this was my own attempt at being artistic of a slide template is back 12 years ago. What happened was I gave a distinguished speaker talk for the Vehicular Technology Society to the chapter in the UK and Republic of Ireland in Dublin, right? So Trinity College hosted me, and I talked about this thing called cognitive radio. So think of a radio that has an AI brain that's telling it what to do. And you might say, tell it what to do. Well, what happens is the idea behind cognitive radio at the time was instead of a human trying to find, you know, the best carrier frequency, the best frequency band in order to communicate a signal between it and another radio, let the AI figure it out, right? Oh, signal strength? Let the AI figure it out. Transmission rate? Let the AI figure it out. Hey, I'm receiving a signal, but I don't know what it is. What sort of equalizer should I use? How should I treat this signal? What sort of signal processing? Let the AI figure it out. So instead of the human tweedling knobs and looking at the data and stuff, let the AI do that for you, right? And so 12 years ago, there was a lot of buzz about this thing called cognitive radio. And in fact, the term cognitive radio was coined in 2000 by a guy called Joe Maitola. He's since retired, but he did his PhD at KTH, so it's the Royal Institute of Technology in Stockholm, Sweden. And his thesis, you can download it if you want, his PhD dissertation was called Cognitive Radio, that describes the software architecture for basically having an actual thinking radio that does all this optimization and sort of parameter sort of tuning for you, okay? Now, I talked about in this, this invited talk in Dublin, I talked about the advancement of technology, right? We had computers that filled rooms decades ago, and now they're like, you know, tiny little chips the size of like a quarter, right? We talked about the advancement over every decade, which aligns very closely. Like people wonder about the advancement of wireless technology. It's very correlated to the advancement of computing technology. We hear a lot of like stuff, like whenever we, like for instance, we heard about the CHIPS Act. Like how many people have heard about the CHIPS Act, right? So this was an initiative, I think it was about 4 or 5 years ago, to support the US semiconductor industry and, you know, make fabs, really increase the US competitiveness in this global economy, you know, make further advances in microelectronic and semiconductor technology. And what's the first application they always talk about? They talk about cell phones. They always talk about cell phones. They always talk about cell phones. And the reason for that is wireless technology is always advancing at the rate of semiconductor technology. And this chart here, which was one of my first textbooks I published, shows that progression of like, you know, let's say like, you know, analog, you know, sort of soldered radio systems with discrete components, and then you begin putting in some embedded technology, some microprocessor technology, and then it does a few things. So you go from hardware radio, right, like, you know, static, not programmable, discrete components, and then we evolve from the mid-1960s, mind you. So this is already, you know, quite a few decades back. Software-controlled radio. So the tuning, well, let the software tune it. It's not smart, but you say, if you receive, let's say, this signal strength, tune your amplifier or your low noise amplifier to this parameter or something like that, right? And then about a decade and a half later, right, with a few more advances in computing technology, let's go to software-defined radio. And software-defined radio is important because whenever I teach my undergraduate students, like most people, when you think, I'm not sure how many people, you're all here, so you probably love wireless communications like I do. When you think of a radio system, what's the heart of a modern radio system? Any guesses?
Computer.
Close. It's the analog to digital, digital analog converter. Like that's the core. And yet, if you look at a lot of textbooks and stuff, and the way I learned it, right? So, like, I refuse to be the individual that teaches it this way because that's how I was taught it, and then probably my professor taught it that way because that's how he or she was taught. No. So, what happens is the heart is the analog to digital, digital analog converter. The conversion of the electromagnetic signal, maybe down converted or it's going to be up converted, transform into discrete signal, and then that is what's processed by software. So, okay, now I need to make a quadrature amplitude demodulator. I need to implement an equalizer. I need to, do something like, like make a low pass filter, you name it, like any sort of signal processing, maybe an orthogonal frequency division multiplexing or OFDM transceiver. All of that now, with the computing resources, like computing technology we have now, even back in, like, when was that? Mid-1980s. The computing technology back then, with the analog to digital, digital analog conversion technology back then, all of those algorithms, all of those blocks are all implemented in software. Now, mind you, the analog RF front end, the up conversion, the mixers and the power amplifiers and stuff, that's still hardware. But everything in the digital side is now all computerized in software. And now my kids, right? And I mean my kids as in my students. My daughter, I will love it if she goes into electrical engineering. She's 6 now, but there's lots of hope. She just has to stop watching Bluey. But the idea is my students, right, are ECE majors, CS, computer science majors, robotics, math, and as long as they know how to program in Python, they understand a little bit about computer engineering, how to target an embedded system, and they know and they understand. The most important thing is translating the wireless world into software. They understand, like, this is what the outside world, and they see how those beautiful electromagnetic signals, once it's in baseband, get transformed into digital samples and vice versa. That's excellent. Because then they can say, oh, I want to extract out only this information. What can I do? And then that's where I guide them. I say, here's some tricks you can do. Because an engineer, I say this in all my classes, I'm going to say it here too. Engineers do for 10 cents what everyone else does for $1. What happens is, what are the things you need to do with that sampled information? Let's say you have something that's 1 gigasample per second. That's your analog to digital converter. You're getting a ton of this data. Wait a minute. I'm taking that data, and it needs to fit through a USB cable, which doesn't have that capacity to take all those samples. What do I need to do? I need to be very intelligent in throwing away anything redundant. I just need the raw, basic information. It then ends up somewhere on a software program or software environment, and then that's when they begin playing around and manipulating and understanding, and then they see their first few information bits, right? The equivalent of hello world, right? So this chart, I know I spent a lot of time on this. This chart shows, and it's kind of important, like this point here, the software-defined radio, it kind of ties in. There was a Department of Defense project that was looking at trying to come up with a way of doing interoperability between different Department of Defense communication standards, right? Instead of having one radio for Army and maybe one specific communication standard for the Army and 2 for the Navy and 1 for the Air Force and maybe for the Coast Guard, and then how do you interoperate them and you have some sort of switch, why not have it in one programmable radio system that kind of interoperates between each other, like a universal translator? How many followers of Star Trek are here? I hope raise of hands, like, So this is what I mean by software-defined radio anatomy. Of course, I think the green line should actually be right down the middle between digital and analog, analog and digital. So there's the RF front end, which is magic land, right? Like power amplifiers and the up conversion stage. I don't know any of that. And antennas, no, just kidding. I know a little bit of that. But I have colleagues that are way better than me at that. But then on the other side, this green box is all in software. My kids right now, what they do is they actually put this on their laptop. So back in the day, you have a server, it has to be high performing, it's probably Unix. Nowadays, Linux is a great environment, I absolutely love it. But now my students, they run their experiments in Linux, but it's in a virtual machine inside a Windows operating system, and it runs modulation, source coding, compression, channel coding, equalization, all your filtering, your signal processing in order to transmit as well as receive that signal. And it's all done in software, right? And what happens is now these kids, right, have it on their laptops. I lend out a radio. It's only $200, but they can buy it if they want, and they can transmit and receive their own signals. They can design their own communication systems. The way I teach my class now, they build at the end of 7 weeks. So did I mention WPI teaches in 7-week terms? Yeah, 7 weeks. Because because the thing is, it's never a dull moment in those 7 weeks where you teach every 50 minutes. And what happens is, at the end of 7 weeks, they can build a Bluetooth low energy receiver. The same Bluetooth technology that you have on your headsets, your mice, things like that. And they understand it, which is really awesome, right? And then hardware, like these are old photos, right? So this is what a software-defined radio looked like back in 2012. White box, inside there's a green board, has little pinouts and things like that. And then I mentioned Joe Maitola, and everyone says, yeah, Maitola was the one that coined the term cognitive radio, the thinking radio, right? So very important. But what was interesting is back in the day, what was the cat's meow, if you will, of AI, of like artificial intelligence and machine learning? It was genetic algorithms, right? It was like, oh my God, genetic algorithms. You have a bio-inspired algorithm? Oh, genetic algorithm. What happened? And then what happens is, just like every other sort of AI sort of spike, things begin to peter out a bit, blah, 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 and then we go into a winter and stuff. Oh, a genetic algorithm, really? And what happens is, of course, then everything began peaking up again with reinforcement learning and deep learning and all these, and generative adversarial networks and things like that. So these new AI techniques. Now, the way a cognitive radio is, I mentioned it before. It's like you look at parameters of your radio that are important to you, and then you sort of tune it to how you want to optimize the performance of that radio. And that's all done by an intelligence on board. And then what happens is the radio can't just do anything. The radio has a certain set of blocks, building blocks that it can build from, right? And then, very importantly, the most important thing, it's shooting for something. The radio just doesn't do something. It doesn't look at stuff, tweedle some knobs, take some parameters and does stuff. It's trying to optimize something. What's the most important thing that, let's say, your cell phone's trying to do? It's trying to make you have the best possible experience. Really, right? It's like, who cares if your data rate's the fastest? If, let's say, you're like with your grandkid, right? Or in my case, my kid, and all of a sudden it's like pausing, it's pausing, it's pausing, it's pausing. That's a really negative experience for me, right? It's like, and my daughter's like, Ma, I don't think Daddy's there. It's very frustrating, right? Like, what happens is that target experience is a lot more elusive than one would think. It's not just like, hey, high data rate. There's several things. Data rate, there's also the error performance. Perhaps there's also like, what's the most important thing about any cell phone? Battery life, which I'm so guilty of because the number of times it says, boop, low power, it's like, I'm so guilty, it's like, and then I'm like scrambling to find like an outlet and charge this thing, right? But those are real sort of target experiences. So your cognitive radio will optimize the performance of your device, your experience, based on what it sees, what's important to look at, and what it can tune. You can do some little tricks with the radio in order to achieve that, right? And so that was back in 2012. Nothing in terms of the concept has changed, but the algorithms have. Okay? So now we go to today. And so also today's world is a bit weird. So I am, like my degrees, so my undergrad, my master's, and my PhD were all in electrical engineering. I was a couple years ahead before all these universities began changing to the bachelor's into electrical and computer engineering, the master's of science in electrical and computer engineering, the PhD in electrical and computer engineering. So what happens is computing technology has really ramped up, like exponentially so, right? Luckily at WPI, this is my sales pitch, anybody who wants to send kids over to WPI, we offer a bachelor's not in electrical engineering and a bachelor's in computer engineering. It's a bachelor's in electrical and computer engineering because you need to have both, right? And I think as a wireless communication person, it's not just the understanding of the wireless world. I got to know that. But I also understand a little bit about AI. I need to know a little bit about computer architecture and embedded technology. I need to know how to develop software. When you build a house, you need to know more than how to use a hammer. First of all, you shouldn't have a hammer. It should be like a pneumatic nailer, but also how to do concrete, how to do roofing. I just got a welder. I can't wait to use that. And what happens is today's wireless communication, folks, just like in my class last year, right, in October to December, my 7-week term class, it was a mix. And then what happens is, being devious as I am, I said, let's make teams. Let me decide. And then I looked at the class roster, and I intentionally matched up ECE with math with CS majors together because they all bring these skill sets that I think today's wireless communication engineers need to bring to the table. They need to know about the digitizing technology. They need to know about the analog to digital and digital analog converters, right? Luckily, our hometown hero, we have several great companies in the area. The big one is obviously Analog Devices, it's in the name. But there are a lot of companies that deal with A to D, D to A technologies, right? Microprocessing, and what I mean by that is embedded technologies like Raspberry Pis or ARM processors or Arduinos, you name it. But today, today is actually the deadline in the undergraduate calendar for the submission of senior design capstone projects. And I was reading my last few reports this morning. And here I am. I'm a wireless person, and I'm trying to go through embedded code for an Arduino, which is one of those microprocessing technologies, right? But I have to be savvy in that because that's one of those skills I need to make this house. Software, you name it. Well, here's the thing. We're being recorded. Shucks. What happens is ECE majors don't program well. And that includes me. But computer scientists, they can program they swim like sharks, right? But then that's where you have ECE majors that know somewhat programming, but the discipline programming methodology of a computer science person combined with them is excellent. That's why it's very important to have that combined skill set. And then this last part, this is the new part. Right now, a lot of my grad students do this, all my PhD students, you're allowed to take grad courses outside of your PhD program in electrical engineering. All of them go into data science or computer science or in math, and they look at things that are related to AI, right? And relevant types of theory and such. And now we're beginning to see AI classes at the undergraduate level, especially in electrical and computer engineering, and our students are learning that. These are kind of those necessary skill sets, right? So, and then this is shameless ChatGPT generated artwork, because people say, what does a software-defined radio look like? And I have to admit, it looks boring. It's I show you the white box, essentially, it's a circuit board, but it's programmable, but you can make any communication system you want out of it. There's within the capabilities of the hardware, right? So you can't make with a simple software-defined radio a 5G base station. That's not possible. But if, let's say, you understand your hardware, you understand your tool, you can build wireless systems in software, right? And what's interesting on the computer science half, the part that I'm not, right, but I'm very aware there's something called software-defined networking. So your computer networks, or routers, your switches, how does your communication global network? It could be a bunch of fiber backhaul, everything like that, is also becoming very flexible and programmable and stuff. Oh, there's a disruption in this part of the network. Oh, that's fine. We'll reroute around that disruption. And there seems to be a convergence of the programmable wireless technology and the programmable networking technology. So it's becoming kind of blurred, right? So this is where AI is coming in. If you say it's kind of taking over humanity, okay, fine. I admit it's taking, but the reality is it's doing stuff that 20 years ago, 15 years ago, it was all manual. Right now, the way we're implementing it, it's capable of doing stuff that human-operated networks could not do. Not at the speed or scale or efficiency as what this technology can. Okay? And the thing is, very importantly, and this is what's great about WPI, I know a little bit of self-promotion of my institution, what happens is the silos between these disciplines are also going down. So there's really not like, I'm a wireless person, I know electromagnetics. I'm an embedded person, I only know embedded technology. Now everybody knows a little bit of each. There's, let's say, a strength in one, but there's an understanding of several, and that makes for a much better skill set. So let's say my concrete making abilities for making a house, it's not strong, but I can definitely do electrical work. And then I have a friend who's a civil engineer who makes excellent concrete, but only knows the basics of electricity. Hey, no. Okay, enough house analogies. Now you know what I'm thinking about for this weekend in terms of things to do around the house. So applications that I deal with, right? So for instance, one thing is space communications. And in fact, it's actually, these slides are out of date. Like for instance, I forgot where I read this online. So it seems like, for instance, I forgot who it was. Maybe it was Starlink. They currently have, if I'm not misquoting, so don't quote me on this, but I think between 25 to 50,000 of those CubeSats, LEO CubeSats in orbit right now. They showed literally, here's the globe, and it's just like covered in all these dots. And they say it's not to scale, but they have that many, and now you have several other companies jumping in, and as well as countries. You have China going in, you have the EU going in, you have Amazon starting to launch. So imagine now, like space, right? And you might say, why? Well, because these satellites can provide that wireless connectivity that you might be in what we call like, what is it called? Like I called it a spectral desert. But basically, if you're in an area that does not have broadband coverage, this is a fantastic option, right? Like, so back in 2009, there was a conference I attended in Germany, and Joe Maitola gave a talk. And it was great. He says, the future is going to be satellite communications. I said, really? No, it's too expensive. And I was thinking big, monolithic, many hundreds of millions of dollars, takes 10 years to develop, radiation-hardened satellite platforms going up. And I said, there's no way at scale to cover the planet, to provide everyone broadband connectivity. Would this be even possible? But disposable CubeSats? So CubeSats, they could be a cube, but they're more like this, right? They're like, so they're rather elongated, tall, like, maybe a foot long, 4 or 5 inches wide, 4 and 5 inches wide. They'll have solar panels, and these will be equipped with wireless technology. And what you do is you develop what they call constellations. You launch them in pods. They distribute. So there are videos online showing how these are launched, and you'll see a string of pearls in space at night. And they distribute into constellations, and if you have a lot of them, like thousands of them, that can provide that reliable wireless connectivity on the ground below. And I mentioned rad-hardened. Rad-hardened, radiation-hardened, if you have space weather, right, and so let's say solar flare activity, and it fries some of these satellites. So the chemistry of these microchips and these boards and stuff is slightly different than your commercial devices. So it's like at least a little bit more robust to things like solar flare activities. But it's expensive to develop this hardware to be radiation hardened against space weather. And so what ends up happening is, where am I? My thought. Yes. even if you lose some of these, and there are some videos of that happening too, no worries. You just launch a few hundred more. It's way cheaper than developing a whole brand new big satellite to put into orbit. Now, that's great. But now, can we take it one step more? And instead of just having wireless signals come down and wireless signals goes up, can we also put that AI to make those wireless signals intelligent, right? Because the Earth is a really big place to cover, right? And conditions may vary, right? In terms of how well you can receive that signal from space, right? So what we did is in collaboration with NASA Glenn Research Center. So that's in Cleveland, Ohio. So yeah, Cleveland rocks, right? So what happens is at NASA Glenn Research Center, we had this project on the International Space Station. It's since been that project's been decommissioned. They had 3 software-defined radios on the ISS. And they said, could we put AI on those software-defined radios and look at creating adaptive wireless communication links? So let's say there is a solar flare activity. Let's say there's more interference. Let's say there's something that's messing up your communication link between Earth and the ISS. Can you have radios at either side be intelligent to come up with a way to bypass the interference, to increase signal strength, to lower data rate, to make a more robust communication link and enhance performance? So that's what we did. This diagram here is one example. This actually came from the master thesis of Max, one of my MS graduates, that showed kind of one of the concepts. So you have the International Space Station. You have TDRS, that's a U.S. government satellite that helps with a lot of positioning and navigation, but it's in deep space. White Sands ground station, that's in New Mexico, and then GRC, that's in Cleveland, Ohio. And what we were looking at were different communication frequency bands. Ka band would have been great, but it's kind of a little bit high frequency, 24 gigahertz. We have S band, which was a little bit better, Ku band, and all that jazz. And what we were looking at is, okay, let's start simple, and let's only look at simple parameters like the data rate, because if, let's say, things get bad and you want a really reliable communication link, you transmit slower, right? It's the same thing like with talking with somebody. Let's say it's very noisy. Let's say my father-in-law, we were driving down here, and I can't hear him because the windows were down and we were playing music really loud, and I can't hear him, or he can't hear me, and I just talk slower. Oh, okay, I get you, Alex. I never talk slow, but But what happens is this work was actually published in IEEE Spectrum, in August 2020, right? That describes about, this was a 5-year project with NASA, Glenn, as well as my friends at Penn State and WPI. And what we did is we built our own AI architecture for space communications between the Earth and space. And what's interesting about this is we tested it on some very simple parameters, transmit power and data rate. But the architecture can be expanded to things like packet size, routing performance. Let's say you want to change the size of the preamble. Perhaps you want to use a different cyclic redundancy check. Perhaps you want to use different encryption techniques. You can try a variety of different things at different layers of the protocol stack. But we were just doing a proof of concept. But we developed this, and then what we did with it is we then looked at, in particular, something called reinforcement learning neural networks. So RLNN, the way it works is you have the agent, that's your AI, right? And what it does is it says, I'm going to take an action, I'm going to do something in this situation, and then that action by in this case, your wireless communication system, then operates in the environment, right? In this case, the space communication channel. Then what you do is you say, how did my radio do? How did the overall communication link look like? And what's my reward? Did it do good? Was it really beneficial? And what state is my radio in? It's am I in a better state or I'm in a worse state? And then it goes back to the agent, and the agent's oh, didn't turn out so well. Let me try this again. Another parameter, another action. and then try it again and go into the environment, and just do that over and over and over again, right? So what happens is my agent learns through reinforcement, through trial and error, okay, about like, my actions done in this environment. Now, what RLNN does is before my agent does anything in the real world, it tests it out on a fake environment that's implemented on a neural network, right? So neural network is essentially, if I can't have a mathematical expression saying, if I do this, what's my reward, okay? So generally, like, if I take an action, I can write a mathematical expression and give me a value between 0 and 1, for instance, 0 being awful, 1 being awesome, and say, if I do this, and this math expression characterizes the environment, what do I get? So let's say I use this data rate and this transmit power, 0.3. Oh, that's awful. Pfft, no way. How about I use this data rate and this transmit power level, 0.9. I think I'm going to keep it. I'm not going to go any further, right? It's like, don't go above 1. No, just kidding. But what happens is in life, you sometimes can't write a math equation about the environment. What do? You use a neural network. So neural network essentially basically will create an input-output relationship where you feed in the actions, you get the reward and the state out of it, and it's supposed to represent the environment, right? This thing here that your radio, your agent is operating on. Now, the thing is, what's special about the neural network? Or what's the problem with the neural network? What's the number one thing that everybody loves about neural networks? It's only as good as how well you train it. Because the thing about the way neural networks work is essentially with a neural network, you have to give it data of like the environment that you're operating it, and you have to train it, and saying, you got it? Are you accurately mapping the actions to rewards? And the thing is, if you don't train it enough, you don't use the right training data, if the environment has changed or anything, your neural network's useless, right? So usually my students, no problem, 5 minutes, well, I'm exaggerating. I say 5 minutes, they'll say it usually is a few days. They implement the neural network or the machine learning, but then they spend the rest of their PhD about the training and the training data. That's what it always comes down to. It's the training. One of my PhD students, Shrikant, my first PhD student, he came up with a machine learning technique, and hey, that's great. Now, what about the training data? And that was basically the rest of his PhD, was like coming up with how to train it. Because that's the thing. It's not a mathematically tractable solution. It's trying to mimic one, right? The input-output relationship. Now, the thing is, just like what I mentioned, what happens if the environment changes? That neural network no longer maps to that environment. It's going to give apples and oranges responses, right? So what you do is you create what they call an ensemble, or a collection of neural networks, and then you have to decide which one to choose to match to the environment, right? Which one best fits, and then you test your agent out on that neural network before you provide the action it thinks is the best possible for the environment. And then there's some really big practical issues like catastrophic forgetting, which is an artifact of that training. Again, if most of my students, finding an AI algorithm part's the easy part. It's the training part that's usually the hard part, right? Or the training data is corrupted or needs to be cleaned or something. It's always that. It's not really the algorithm itself, right? So hardware-wise, what we did is in the SCAN testbed, that's the NASA SCAN testbed, that's on the International Space Station. What we did is we used a DVB-S2 transmitter waveform. So that's the digital video broadcast satellite version 2 transmitter. And we used a BPSK receiver waveform for receive, and we used S-band. And then we use the BPSK half data rate. And then on the ground station at Glenn, Again, we used, this was the fun part. So my students actually spent some time at Glenn for about a month. We implemented our architecture on an FPGA, right? So an ML605. And then the cognitive engine workstation was integrated into all of this. And then we had a couple of satellite radio modems as well, like one from Viasat and one from NewTek as well, in order to implement the communication with the International Space Station, right? So really, we had some conventional radios, and then we threw in the AI engine here and integrated in part with the FPGA platform as well. But that took a little bit of time, like, you know, about a month. And then, of course, you know, satellite communications. It's like the International Space Station's not always in the same place. It's going around, like, what, 18, 19 minutes per orbit or something like that? Something wild, like, you know. And so what happens is you got to get it at the right point. Like, you know, this experiment fails if you don't have line of sight with the thing. So then we had to figure out when was the best time to do these experiments. And we found these windows of opportunity. They're usually in third shift. And then we run the experiments. We collected the data. And then afterwards, some of the data was kind of corrupted. It didn't make sense. And then and that's the thing. There was collecting data was the easy part. It's the cleaning up of the data and making sure it's usable. That's the hard one. All right. And then this explore and exploit. This is also something about what is it called? Artificial intelligence. It needs to learn. Okay, so it's exploring. And then once it learns, it does stuff, and that's the exploitation part. And that's what this chart does in particular. Like, we were looking at things like jitter versus, you know, for the different types of algorithms that we were using here to avoid the catastrophic forgetting. All right. So that's satellite. So that's in space. Let's come back down to Earth, although 5G is also in space, but I'm not going to go there. And then 5G and 6G. So 5G networks are complicated. So, you know, and I mean, the thing is, people ask me, what's the difference between 4G and 5G? So 5G contains 4G. So 4G was more or less strictly a cellular network. Sure, there was some Internet of Things. But then 5G came along, and it basically says, I'm going to be the cellular network of everything. I'm going to be a cell phone base station. I'm going to be an Internet of Things protocol, right? I'm also going to be millimeter wave. And I'm going to be everything in between. I'm going to be also side channel, device to device, V to V. So you might say, what do I mean? So cars talking with each other directly, vehicle to vehicle, right? D to D, device to device. It's not Dungeons and Dragons or whatever that is, but it's like means like two devices talking directly with each other without talking through a base station. Millimeter wave, a lot of people have heard of millimeter wave, is a very not typical cellular frequency band. You know, we're talking about 60 gigahertz. That's like an order of magnitude higher than most carrier frequencies that cell phone technology uses. Obviously, we have the cell base station. And then IoT. How many of you have bought a really fancy microwave in the last several years? No show of hands. Oh, you folks are way better than me. Like, you know, my microwaves die all the time. So my mom bought a microwave, like, I think a year or two ago. First ever. My mom was like very serious. It's always about oven, cooking with the oven and stuff. And then she called me and she says, what's this thing about setting up Wi-Fi? And it's true. Like, nowadays, like refrigerators, thermostats, microwave ovens, lights, everything is all connected, right? And right now we're just beginning to see this sort of hyperconnectivity of all these different electronic devices all interchanging with each other. And the idea of 5G is everything's going to be a cellular device, or at least underneath the same cellular network. Right? So now your microwave oven is going to be the same thing like your cell phone, like your iPad, like your car, like your toaster, like your thermostat. Everything will look like a cellular device. There's a lot of security concerns, obviously, around this too. Like, for instance, how good encryption does your microwave oven have versus your cell phone? But the idea is that's the difference between 5G and 4G. 4G was strictly like iPad, laptop maybe, cell phone, cat videos, right? And 5G is like everything. And then 6G, the difference is 6G now, AI controls everything. Because right now, everything is like a 5G device, but they don't really play well with each other, but they're part of the same network. 6G, the AI will enable them to play. Yay. So this is what it looks like. So 1G, anybody have a 1G phone? Like, maybe like, no, I'm like looking, maybe we have, but there we go. Yes. Oh my God. Okay, I'm going to pass this slide. No. So 1G phone, then 2G when everyone's like, hey, look, I have a GSM phone. 3G, this was sadly bad timing because when 3G began coming out in the early 2000s, what happened in 2001? The dot-com bubble went. And why is it so close to heart? Because what happened is in Canada and pretty much like in the wireless community, a lot of layoffs, a lot of great companies went under. It was not a good time. It was not a good time, right? Of course, in the ashes, there was a couple of things that happened. Wi-Fi began taking off. Like became, oh, what's this Wi-Fi? What's this 802.11, 802.11b, 802.11a? Why did B come before A? I don't know. And then what happens is 4G mysteriously came along and everyone's like, oh, I have my 4G phone. Do you have your 4G phone? And like, what? You can send email and surf the web on your phone? Like I had friends who had like a BlackBerry with 3G and I thought it was miraculous. They could see an email. I'm like, I can't do that with my phone. And then 5G came along and it talks about Internet of Things. Think your connected microwave oven. AI begins going in there. Oh, the big killer app people think still about 5G? Virtual reality. Like I'm not into it, but my students supposedly cause a lot of damage to their apartments because when they have those like headsets and they do those games, like I think these walls are strong, but I think they don't really use good sheetrock, whichever apartments they're in, right? And then V to X. And then 6G is going to be cognitive radio, the stuff I talked about from 2012. And then massive MIMO, very large antenna arrays. I love the antennas. I love antennas. So when I saw antennas in the back, I'm like, dipole antennas. And then I was going to show in the last part, but like the thing is machine learning is everywhere. This was actually a paper. You can actually download this for free. Look for McClintock and Wyglinski and Wernsing and Ferreira. And this paper says AI is everywhere in your radio technology. Everything from the low noise amplifier, the analog filters, the A to D converters, the automatic gain control, the MIMO control, everything has, like people have looked at AI applied to each one of these different components of these communication systems. And that's what this paper, this tome of a paper, it's like 30-something pages long. Kyle was like quite prolific. He looked at also the different types of supervised learning. That's a type of AI, machine learning AI, used in wireless communications. Things like logistic regression. He looked at SVMs. He looked at RNNs, CNNs, you name it. So one area that benefits, and this, my PhD student, his thesis got deposited today, so I'm super happy. Adriel, he looked at a way of looking at AI in order to fingerprint your wireless devices, but not by saying, oh, who are you? And it says back, doo-doo-doo, my name is, or like maybe my father on that, doo-doo-doo, my name is Bob. No. What happens is looking at the electromagnetic characteristics of the radio frequency front end. So let's say there's a slight electromagnetic imperfection in your radio, the actual radio, like it's slightly off in carrier frequency. Noted. That's an interesting characteristic. So if it finds a bunch of characteristics and each phone is slightly different, sure, it's done to spec and there's quality assurance and everything, but there's all these little imperfections. Fingerprint, 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 fingerprint. Everyone can be fingerprinted. And he looked at how well this could work. I'll pass this slide. How well this could work using AI and examining different features and characteristics. And let's just say there still needs to be work done. Let's say that was the conclusion of the dissertation. It's good, it's interesting, but the third journal paper he also submitted today looked at the effects of temperature. So imagine your fingerprint changing with temperature. So, I need to commit a crime. Your fingerprint looks different compared to so that's the thing. And why? Because then your data set from the AI that's trying to classify your fingerprint says, oh, yeah, Bob didn't come here. No, because Bob, sorry, I'm picking on you. I'm going to have a hard car ride back to Worcester. So the idea is, what we did is we built a nice little test bed called Medusa. I don't know where my students get these names from. So like Medusa, could you choose something a little bit more happy, not like, and what happened was he built what we did is we didn't just buy 100 cell phones and tested them all. And we didn't use theory because theory is as good as the assumptions you make it. What happens is we use software-defined radio technology, and we use this wonderful RF multiplexer, and we basically went through all the permutations of transmitters to receivers in order to see, okay, let's look at all the different types of RF characteristics and then test it, repeatedly with different AI techniques to see how well they classify the RF fingerprints, okay? And that's what under the hood it looks like. It's very loud in my lab because there's a really large server. There's a very large, server next to that that's just screeching, if you will. And so what happens is, what's omitted in this photo is that multiplexer. But essentially, there's 8 software-defined radios, and it's choose a transmitter, receiver, and we just exhaustively test out all possible combinations and look for all those RF characteristics in order to create some sort of pattern for those fingerprints. Where's the loop, if you will, the equivalent from an RF standpoint for that radio system, okay? And we looked at things for instance, we looked at jitter, and then we looked at things for instance, the packet error rate versus amplitude. And what we did, what's really important is we looked at the behavior over days. We just didn't run it in the lab for an hour and say, hey, I got an RF fingerprint. We exhaustively polled these radios to say, did we get the same characteristic? Did we get the same characteristic? It's like taking your thumbprint and you do it for days. And then what he did, and with the help of a portable air conditioner I brought from home, it's let's do this again at 25 Celsius. Let's do it again for 20 Celsius. Let's do it again for 15 Celsius to see the characteristics and if we can fingerprint properly, okay? Okay, so the future, another number, 7G. I'm just so, the wireless community is just, I don't want to say we're boring, but the core thing about this guy, about 7G, is that, so what I mentioned again about AI winters and we have to wait 15 years? So I'm not going to bet money and I'm going to put a disclaimer, do not use this for financial decisions or any other decisions that and I really do mean it, but my guesstimate in 15 years and also looking at trends in quantum technology, it's going to be quantum machine learning. I think that's the next thing. I think one of the main things, and NVIDIA is doing a great job and all these other companies are doing a great job in terms of the high performance platforms that they have in order to do the AI processing and everything like that. I think in 15 years, the amount of data that's going to be out there, imagine also thinking about those humongous IoT networks and everyone's microwave ovens and running shoes and watches and the data everywhere. We're going to need computing processing horsepower on a whole new order of magnitude, and quantum is probably going to be it. Right? And so what happens is, I know, ChatGPT, draw me hyper-connected. And sadly, it's actually not that bad, except the Death Star thing in the background. But the idea is, we just submitted a revision. So the idea of quantum machine learning, the idea is, instead of using binary 1 and 0 as your fundamental unit of information, I'm not a quantum physicist. That's another important disclaimer. The idea is, the way I like to describe it as an electrical engineer, is that the representation of information is a phasor. Essentially, it's so you have a very large continuum of values that can be assumed by that qubit, right? And now the idea is, how does that map to our understanding of that action reward type of mapping, if you will, that equation that neural network produces. And so where would something like quantum and a quantum-enabled machine learning optimization in the communication world come in? It's going to come in here. Suppose you have a really large IoT network, millions of devices, and you want to tune them all. You're going to use this carrier frequency. This carrier frequency during this time slice, and you're going to use the next one. Oh, no, you don't want to interfere with him at the same time. You use a different carrier frequency. Oh, no, I'm going to have to turn you over to that frequency. But imagine millions of these things. The quantum neural network will be responsible for that continuous network management side of things, right? So that could potentially have the capability, but there are huge issues. Like the big thing going to be latency. If you have millions of devices, collecting information and pushing out decisions is going to be like, hopefully I'll be retired by then. Wait, let me think. I'll almost be retired. So, but I'll encourage the next generation of like great professors to carry on that like great task. But the idea is with such a large network and needs to be optimized, you're going to need something of that capability because I think conventional means might not be able to make it. And so we have this journal paper here, and hopefully it will be accepted, that kind of describes using current techniques. So you can actually, I'm trying to think if access is free or depends. Like, so IBM, you can log into their quantum computing, and they have like programming development environments like Qiskit, but you can also have like, there's also open source projects like Torch Quantum, and there's a few other, like, there's one other, NVIDIA has a package actually called QQuantum as well. So there are already packages out there for people who want to do quantum machine learning or quantum computing development, right? But again, I ask all my ECE students, how many of you have taken a quantum course? Zippo, right? And then the quantum people, if you ask them, the quantum physicist says, hey, can you help me? They're like, we're just busy trying to make this thing a reality, right? A computer with a few qubits, great. But we need something with lots of qubits, right? So again, a qubit is a quantum bit, right? That's a unit of information there. So yeah. Qiskit, there's TensorFlow. Oh yeah, Penny Lane, that's a cute name as well. Everyone has to come up with a cute name. But there are quantum tools out there now that people can start experimenting with. I think Qiskit can actually interface with some of the IBM quantum resources. And then we did some similarity results. This is how we validate our research with respect to in terms of how well our machine learning actually optimized. All right, and then training time. That's also important. All right, so closing remarks. So wireless is cool. I'm glad I didn't put anybody. It is. I mean, but seriously, I think the thing is, this AI has been there for a long while, right? But now we're at a point where we can actually do some really cool things with AI. There's still a lot of work to be done. But at the same time, the advances in computing technology has also lent itself a lot to these conveniences. Look, I saw a kid, I kid you not, yesterday. Did I say kid twice in the same sentence? Yes. And I mean, he was on a bicycle. He's a little older than my daughter. I think he must have been in grade 2 or 3. And he was talking on his cell phone watch. Like, how many of you have watched, this is before my time, but Dick Tracy. Anybody know Dick Tracy? Yeah. So here's now a 9-year-old doing Dick Tracy because mom and dad got him a Dick Tracy watch. But that's today, right? How much is that watch? Maybe $300, $400. And also, mom or dad say, oh, Jimmy is like about 3 blocks away. I know exactly where he is. I'm even guilty of it. Very shamelessly so. How many of you have heard of AirTags, right? And so not only, so my wife and I, we obviously know where we are. Usually she's trying to find me to see how late I am home, which is almost all the time. I'm just looking at her dad, so. And then, but I also can trace my dogs. I have a little AirTag in them, mainly because I'm worried they're going to run off into the woods and I'll never find them again because they can do that sort of thing. But what happens is we live in this really connected world. There's still a lot of work. There's a lot of potential. This thing here, sure, this is an image that ChatGPT produced for me. But in reality, imagine things like your microwave oven, like your thermostat, like the world around us, right? These being connected, and like, you know, imagine combining that with that immersive reality stuff. Like, you know, like it's really cool to see this technology in action. Even now, like, you know, being Zoomed and being physically here at the same time. So with that, let's see if I have a closing slide. Yeah, there's my email address. So thank you all for your time. I'll be happy to answer questions. Thank you.
Okay, remember, folks at home, if you want to ask questions, there's a Q&A panel for you to ask questions, and I will take them and condense them and feed them to Dr. Wyglinski on your behalf. So don't be bashful. I'll go ahead and ask questions, and feel free, audience, to ask questions from the floor as well. Well, I'll ask a question.
Yeah, go for it. Yeah.
Okay. So you've seen over time the trend of moving commercial demand for spectrum higher and higher in frequency.
Yeah.
And some of that is, you know, just that's what's available, and some of it is, well, larger bandwidths are available up there compared to what are available down lower in frequency.
Yep.
Do you see this trend continuing, and how hard do you think it can go from a physics standpoint?
That's a great question. So I think the answer is everything's going everywhere. So I think we're going to hold on to the lower frequencies mainly because of like cost, right? Because like we already have the infrastructure in place. It's not that expensive to build a radio that's operating below 3 gigahertz, right? Relatively speaking, right? And you know, like I think we will be acquiring more and more spectrum. We're going to be moving further and further up in frequency band, but we're going to hit new issues, right? So like for instance, there's talk in like 5G of going like over 100 gigahertz, right? Like going into those frequencies, and I'm like saying, why? And there's probably a reason in terms of the telecommunication infrastructure, but it's not quite clear per se, except for the fact that there is a big push for optical communications. So about 15 years ago, no, 15 or 18 years ago, the buzzword was free space optical communications, basically laser comms, right? So, but laser comms is very susceptible to things like fog. There's also issues with laser comms because of the nature of the laser and how focused it is like it's absolutely does not have any resilience in terms of if you're slightly misaligned, right? But in terms of data rate, like it could deliver a massive amount of data, right? Like so, for instance, several NASA missions, like that are supporting like deep space communications. A lot of them are like free space optical, communications, right? But I think that there's those applications. Would I, like in a cellular context, be walking down the street and I have my base station shining a laser on me and such on my cell phone and vice versa? Probably not, right? On the other hand, what happens is I think it's also using more of those advanced signal processing techniques, and especially with AI. Like so, for instance, I kind of went blah, 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 blah to everyone in the interest of time, but I'm going to go back to it because it's really important. This massive MIMO is really important. So we're talking about a phased array of like hundreds of elements that can create pencil beams. Lasers? No, but really focus. And then the AI comes down to, in part, like let's say when your radio initiates, when a hand shakes to a cellular base station. So it, like back in the day, I forgot which technology it is, not spectrum. So like in 2G, the polling, right? And you had your speaker and you had your phone and it's like you hear bzzz ever so often and stuff, right? Your cell phone's polling the base station saying, hey, does anyone hear me? The cell phone says here, and now you're mapped to that base station, right? And that's why when you're driving on Route 2, how many of you have driven on Route 2? Like, yay, everyone's favorite highway in Massachusetts. And then back in the day, in like, the mid 2000s, like, 2007, 2008, you're driving and then your call gets dropped. And then you have to call again and your call gets dropped, the mobile assisted handoff, right? But what happens is with massive MIMO, So once your phone pairs up with a base station, it says, here I am, and it knows the location. The AI, so your phone, the key is to keep it as cheap as possible, because I for one, will not pay for a $10,000 cell phone. I will pay the least amount of money for a cell phone. Put all the costs on the base station. Put all the antennas on the base station. It makes the pencil beam to me. It tracks me. And the reason for that is frequency reuse. Because then if I am very highly spatial to you, I could potentially reuse that frequency somewhere else in another sector in that cell site, right? And another sector, and another sector. The optical communications is the extreme version of it, but it's very tricky when you have a lot of mobility, right? But the optical will also have a wild amount of bandwidth versus, let's say, this pencil beam thing. And then you on the uplink, well, depends on how much data. If you're like sending a cat video up to the cloud, well, then you're in trouble, because usually the channels tend to be asymmetric. So that's one example. So we'll be acquiring more spectrum, but I think it's going to be purpose for different applications. So like, for instance, a millimeter wave, right, that we see in a lot of urban places, right, is usually meant for like 100 feet, 150 feet, but you get like 1 gigabit per second data rates, right? But millimeter wave at 60 gigahertz, you know, if it gets through glass, great, but through a wall, I kind of doubt it. You know, it's going to have to be a really strong signal. So it's very handicapped. On the other hand, like, you know, wireless signals at 2.4 can go through a wall pretty decently, right? Unless it's like shielded like crazy, right? So I think different environments, different applications will require different solutions, and then also the frequency availability. I think what the FCC has done so far in the last decade has been great, freeing up. Like it's been very strategic. Like, for instance, it was very sad for me when they kind of got rid of the DSRC spectrum in what is it? 5.825 to 5.875 gigahertz. Like, it was like 75 megahertz of spectrum. It was supposed to be based on it was supposed to support IEEE 802.11p V2V communications. And that standard came out in the late 1990s, early 2000s, but no one really did much with it, because auto manufacturers are like, why should I do V2V? And then people said, well, what are you doing with 75 megahertz of spectrum? That's empty. And then the FCC is like, fine. And they took it back, right? And then 5G came along, and everyone says, well, cell phones have too much latency. So, you know, how fast do deer move? Very fast. So to get in front of your car, what's a great purpose of V2V? Your car telling the car behind you to stop, because otherwise they're going to rear end you, right? And the worst thing that can happen is latency. Like that car, like, you know, by the time you get the message, deer, it's like you're already exchanging insurance information, right? So the idea, and then what happens is they came up with a low latency version of 5G, plus they also have different modes of 5G. They have something called mode 4, which is sidelink, which allows for cars to talk directly with each other without having to go through a base station. So it makes it faster, right? But the primary purpose of mode 4 is for range extension, not necessarily for that low latency, although that option exists. So great question. So the idea is we're trying to figure out, because no one's going to give away their cell phone, right? So like what I do, and this is really awful, whenever I go to Canada, I don't have a great cell phone plan. Like when I cross the border, what was it? I think it's like $1 a minute for voice. I forgot how much it was for text. And you don't want to know how much it is per megabyte if I use data. It's like really, really, really bad. So imagine, luckily I know my way back to my mom's place in Montreal once I cross the border, but I don't have access to data. I'm like, wow, I don't have access to Google Maps. I can't really Skype anyone or call anybody or anything like that. My wife can ring me, and I'm like, do I really want to spend $1 answering that call, you know, sort of thing? So, but we are so dependent on this technology, right?
We do have a question
go for it.
Fiber.
Yeah.
Mark Petruzzi says, will we continue to use fiber for land-based backbone, and it'll help for the availability of spectrum?
Yes, exactly. So wherever we can use fiber's great, right? But I think fiber, though, is expensive to install. I forgot what it was. What was the cost? Again, I thought it was like on the order. It was like I thought per mile of fiber being installed. It depends how you install it, because one thing that came up was during COVID. COVID was kind of like, was definitely a moment when people were aware that a lot of people in this country don't have access to broadband, right? And then it was like, okay, how do we bring broadband? How do we make it accessible? And people said, well, just put fiber in the ground, until you said, well, it's about like, $10,000 to $15,000 a mile to install fiber or something like that. And it's like, oh, are there other cheaper options and stuff? Fiber's great. Like wireless to fiber is going to transmit fantastic amount of data versus, let's say, like millimeter wave, which is like, we're talking about tens of gigabits per second of traffic. Like nothing beats fiber. But the installation of fiber can be cost prohibitive. That's why when Joe Maitola gave his keynote talk in 2009, I think it was CrownCom. Yeah, it was in Hanover, Germany. He said satellite's the way to go because imagine you're in an area where, I forgot which town this was, where let's say the land all around is basically bedrocks 2 feet below from where your feet are and stuff, and you want to bury that fiber really deep. And oh, by the way, your utility poles are not tall enough to accommodate telecommunication infrastructure in addition to utility, in addition to everything else. So you're like, shucks, do I install new poles across town, or do I, what do I do?
And installing fiber in the vicinity of the San Andreas Fault is probably risky.
Yeah, just maybe a tiny bit. So what happens is that's why satellite, and the thing is it's cost trade-off, right? Of course, now you're putting satellites into orbit, and then there's latency as well and things like that.
Well, this all gets back down to the question of enabling technologies. And
Yeah.
all of these things that drive technology solutions depend upon something coming along that makes them commercially viable. In the
Yeah.
case of SpaceX, it was the ability to recover boosters and launch large numbers of satellites that essentially are expendable.
Exactly.
And these things have come along in waves over time that in fact created the cell phone the same way as technologies developed that enabled miniaturization and so on.
Exactly.
So that's very interesting stuff. Anything else? Any other questions? Well,
Yes, yeah, go for it.
With all these satellites up there, you're talking about thousands.
Or tens of thousands, yeah.
So isn't that going to hit each other?
So the question is,
Doesn't it increase the ambient noise level?
yeah. So the question is, with all those tens of thousands of satellites in orbit, will that increase the ambient noise level? The answer is like maybe, but the bigger issue is what you just mentioned about collision, right? So like even before we had like tens of thousands of these like cell phone satellites, like up in orbit, there are entire programs. Like I had a friend of mine who was on one of these, looking at how do you collect like orbital debris, right? They were even talking about at one point Earth forming actually a ring of these things as they began to aggregate. And these things are extremely dangerous for, let's say, manned space missions. Because like, you're in a space station, and then let's say here's like a hexagonal bolt that was the result of, let's say, 2 CubeSats that collided, they shattered, and now this thing's going at, who knows how fast. And then here's the International Space Station, and goes right. I think the issue of tracking all of these things is going to be a huge problem. And then in addition to that, things like orbital debris becomes a really huge issue in addition to that. So you're absolutely right. And I think that's the number one worry, because like, how do we regulate that? Like, who's responsible for, let's say, okay, this private company's putting an entire constellation. How do they play nice with this other organization putting their constellation and this other organization? This is actually not even like, let's say, within orbit. Like, so for instance, I'm working on a project right now with respect to lunar 5G. So that's actually another big thing, like bringing 5G to the moon. So like for instance, imagine there's a wireless communication link between Earth and the moon, and like let's say some orbiting platform that's, let's say, a free space optical communication link. And then it's a 5G environment down on the moon. So you have, let's say, astronauts, you have robots, you have equipment, and they're all trying to communicate with each other. And And the thing is, let's suppose now you have the US, then you have the European Space Agency, then you have several other countries or organizations that are on the moon. Maybe you have several private companies as well. There's been talk about that. And then, wait, who has, like, do the Earth spectrum regulations apply to the moon? Right? So, like, who uses what band? What's the priorities and stuff? So there's all these unanswered questions. The technology is almost like pushing for these answers in order to deconflict, let's say, the players that are coming into these spaces. Oh my God, is that a pun? Yeah. So, but that's a great question. Space debris is a frightening question too.
So it's a good application for AI.
Yeah, yeah, there you go. Well, I mean, the thing is, like so one of my research areas, like the dynamic spectrum sharing, is, let's say, it's almost like who gets to this wireless channel first, like me or you. And then what happens is the AI says, oh, okay, I'm there first, and then you find another spectrum. There's of course there is the issue of some wireless communication traffic is continuous, like me. I'm just continuously transmitting, like in terms of talking. And then what happens, but there are other people who they talk a bit, then they pause, then they talk a bit, then they pause. And what happens is, what's the issue is that pause might be interpreted by other people as, or other wireless systems as releasing that frequency band to some other application, right? It's in the Wi-Fi world, it's called an interframe spacing, right? So you have a little gap, and then you can engineer the gap to be really small so nobody can sneak in, right? But it's like, how do people navigate sharing that wireless spectrum, especially if it's from different entities that don't necessarily have to collaborate with each other, right? So on Earth, you know, the UN has like the ITU, right? Yeah. And so if you look at a spectrum chart for Canada, for US, for UK and Ireland and every other part of the world, like, you know, television spectrum is generally in the same place, radio, there are some variations, but then again, we need something similar for, you know, other planets, right? Because imagine, like, you're on a mission critical, like, you know, doing something mission critical on the moon, and then you can't communicate because there's wireless information from that person's project over there. So, great question.
Thanks everyone for joining us tonight. It's been recorded here, and in a few days, the program will be available on our YouTube channel or via the website, chathammarconi.org. Thank you again, and good night.